Resume recording. Okay, good morning to you all. Another session. Today we deal with sequential circuits. Today we deal with sequential circuits. I think this is the last topic. I'll probably just briefly go through the last two, I think, major topics of your course outline. But sequential circuits design, sequential machine fundamentals will remain the last that I will go into a bit deep. The rest of the course outline, I'll just pick a few things. I won't go through that too much. So we are almost done. Hopefully by next week, beginning of July, we'll be done with the course. Right, sequential circuits. All this while we've been dealing with what we call combinational circuits, and we define combinational logic or a combinational circuit being a circuit whose output depends only combinational output only depends. So the output depends only on the present inputs, only on present inputs. Combinational circuits, the output depends only on present inputs. Example, an adder. If you have an adder, you have two inputs, A and B, two outputs, sum and carry. The outputs, these ones, would depend on what the inputs are at the present time. So if I have a 0 and 1 here, it means my sum will be 1 and 0. Present inputs only. We have a case where the output will depend on the present and the past inputs. And this is what we will refer as sequential circuits. Sequential circuits, as I'm saying, it's still not clear in my head. So I'm hoping once it is clear, it also be clear to you. Sequential circuits. So for sequential circuits, the output depends not only on the present inputs, but also on the past. So this is output depends on present and past inputs. The difference being here, present and past, here we have present only. Right. In combinational circuits, soon as the inputs are changed, information about the previous input is lost. The circuit has no memory. Right. A combinational circuit is a circuit which we say it has no memory. Combinational circuit, CC, it has no memory. I gave an example of an adder. So two inputs, A and B, two outputs, C, S, and C. As soon as the inputs are changed, let's say we begin with 0, 1 input, we know the output will be 1, 0. Soon as we change here, the inputs, these are inputs 1, these are inputs 2. Soon as we change inputs to 2, these ones will be lost. It has no memory. So as soon as we change, we now have 1, 0. This changes also, what does it become? Well, it's, let's say it changes to 1, 0. It doesn't change, but it does change to 1, 0. No memory. For sequential circuits, however, SC, they have a memory. Sequential circuits, they have a memory. This whole topic will be dealing with this memory here. This is what we'll be dealing with. We'll be dealing with that memory. All right. Logic diagram. Logic diagram of these two. We have combinational circuit. We have memory. All right. We have our inputs. These are our primary inputs. Primary inputs. We have our primary outputs. Primary outputs. All right. This is what we call combinational circuit without this thing here. This is the combinational circuit. Primary inputs, primary outputs, no memory. When we talk of a sequential circuit, though, we insert what we call a memory. Now, what you have past values of the inputs. So the memory, we have values like this. And now you have combinational circuits. Now I have these inputs here. Now this becomes my past inputs because they are coming from the memory right here. And this whole thing is a sequential circuit. So as you can see, a combinational circuit is just part of a sequential circuit. We have a combinational circuit here where the present in the outputs depend only on the present inputs. Once we insert a memory, we now have past inputs being fed into the circuit. And as a whole, it's now a sequential circuit. All right, we'll give examples later on. Let's talk of comparisons. Comparisons between combinational and right, comparisons between combinational circuits and sequential circuits. Number one, sequential. In sequential circuits, the output depends only on the present input. In combinational circuits, only present inputs. In sequential circuits, the output depends on the present and the past. One, present and past, present and past inputs. One comparison depends on this, the present and the past inputs. Combinational circuits, present inputs. Sequential circuits, present and past. Number two, sequential circuits, they have a memory unit. Combinational circuits, they don't have a memory unit. Another comparison depends on the memory units. One of the two has a memory, the other does not. In terms of speed, combinational circuits are faster. Speed. Combinational circuits are faster. Why? They don't have a memory. So whatever changes which happen at the present will be the changes which happen in the output. With sequential circuits, however, the changes at the present input may wait for what happens in the memory, then there will be changes in the output. But that waiting, that's a delay right there. So logically, combinational circuits are faster than sequential circuits. Now we have design. Combinational circuits are easy to design. Those adders, those multiplexers, they are very easy. When we now talk of counters, how do we count 1, 2, 3, 4, 5, 6. That's a sequential circuit. Very difficult to design. You will see with time how that goes. Comparisons with classifications. With classifications of now these are classifications of sequential circuits. Right, sequential circuits can be classified either as synchronous, or asynchronous. When we talk of synchronous, it means there is a clock somewhere there. There is time. Synchronized. It goes with time. Here, we don't have a clock. There is no time in asynchronous circuits. That's the difference. Definition. What is the difference between synchronous and asynchronous sequential circuits? The difference is here. Right, synchronous sequential circuits change their states and output values at discrete instance of time. So for synchronous circuits, synchronous sequential circuits, these are synchronous sequential circuits. They change their output or states. So states change depending on its discrete time intervals. At discrete states change at discrete time. The state changes at discrete time. For asynchronous, the state changes with change in the inputs. Change in inputs, change in outputs, or states. Right. For asynchronous circuits, the change in the inputs means there is a change in the state or change in the output. Right. What do I mean by that? Back to our diagram. For combinational circuits, if the input changes, the output changes. For asynchronous, for asynchronous sequential circuits. So if the input changes, the output changes. For synchronous, however, there is an additional thing. We have a clock which is attached to my memory here. We have a clock, CLK. So the change in the output is being synchronized by this clock. If the clock changes its state, it means the output will change. Even if we have an input here, this input will not trigger a change. The change will be triggered by the clock so that the whole system is synchronized by the clock. Difference between synchronous and asynchronous circuits. All right. Example of a sequential circuit. We have an example of a sequential circuit. All right, let's say for a counter, we want a counter which counts from 0, 1, 2 to 9. So we have a counter 0 to 9. How do we make that counter? We have a block diagram. This now represents a number of gates inside. This square, whatever it is, it means there are a number of gates inside. If you are given a problem, you can solve it using this way. All right, so we have my memory. I want to design a counter. All right, my memory has past values. Now this is my whole block, the sequential circuit. Right. And here I have my output. I want to design a counter and see how this functions using logic gates. Right. My counter, I input a 0. I want to make a counter which counts from 0 to 9. If I input a 0 for my counter, and I have a combinational circuit which is a 1. So what this means, if I add a 1, I get a 1 here. My first output. And you get a 1 on the out. If I want to continue, however, let's put a clock. Let's put a clock. If I want to continue counting, I take this 1, right? I put it in memory. When the clock triggers a change, this 1 comes back here, and another 1 is added. If I add a 1, I get a 2. My output is now 2. 2 goes into memory, past value, 2 plus 1, 3. Output 3, and it continues until you get to 9. That is how a sequential circuit functions. So inside here, you have logic gates. Inside here, you have logic gates. How do you design something like this? The problem is I need a counter 0, 1, 2, 3, 4. How do I design a gate which adds a plus 1? This is an adder. I can say this is an adder. Something which adds a plus 1. It can be an adder. Inside the memory here, we have what we call flip-flops. We will be designing these flip-flops. But I'm sure this part, the combinational circuit part, everyone now is able to do that. Adders, comparators, multiplexers, everything that we did, you are now applying it in these counters. This is an example how a counter functions. What we'll be focusing on in this topic is designing of these flip-flops, the memory part. How do we design this memory? The combinational circuits, we are done with that. Truth tables, logic expressions, Carnot maps, minimization, then I design my circuit. Provided you have, not provided, if you have a problem, you offer the solution. How do you do that? We go through that a lot of times. Combinational circuits. Now we are on the designing of the memory parts, which are the flip-flops. A basic memory element. Basic memory element, we have basic memory, right? A basic memory element. The memory is called a flip-flop. Flip-flop, what is a flip-flop? I think anything that stores memory, nope, that stores bits, it's a flip-flop. Storing bits, that's the memory part. How can we store a bit? For example, let's say we have a 1, our bits, we have zeros and ones. So this is 1 bit. We have a circuit like this. Right? We have our feedback here. Right. I want to see what is the output of this circuit. If I have a 1 here, it means right here, what do I have? Participation. These are not gates. These are not.
0.
I have a 0. Here, what do I have?
A
1.
I have a 1. That means I've stored a bit. If I have this circuit and I want to store a bit, I can use this circuit to store a bit. It means every bit that comes in here can be stored in this circuit. It comes out the same. So that is a basic memory element. how you can make a memory. This is where computers began, ladies and gentlemen. A computer, it has memory. A memory of my computer is how much gigabits big. These are the gigabits right in there. But this one only stores 1 bit. Gigabits is how many? 10 to the power 12. I think so, around there. It stores 10 to the power 12. Is this gigabits? How many does that mean gigabits? I think so. 10 to the power 12. I'm hoping it means that. So a gigabyte memory, it stores how many bytes? 10 to the power of 12. Information. What is this? It's information. The zeros and the ones, they are information. All right, basic memory elements. State of the circuit is stored in the memory, that is the latch or the flip-flop. This is called the latch or the flip-flop. Same thing, there's a difference. We'll get through the difference between a latch and a flip-flop, but both, they do the same thing. They store bits. These are the memory elements. All right, basic memory element. We are done with that. Let's go into latches and flip-flops. What is a latch? What is a flip-flop? A latch is a basic element of storing information. A flip-flop is a basic element of storing information. So we have a latches and flip-flops. I have to admit, Zenuzai is my latch and my flip-flops. However, because I'm teaching it today, though questions, I did pass, but I never understood what I was doing. This is very critical information. You can pass, but never understanding what exactly you are doing. It's not a miracle, it's possible. I'm hoping you fail, but you understand what I'm teaching here. I don't care. Even if you fail, but I want you to understand what exactly you are dealing with. All right, these are the basic elements of storing information. The major difference between the latch and the flip-flop is the way in which the state changes. These two, latches and flip-flops, they are the same. In what way? In the way that they store information. They both store information. The difference between the two of them in how the state changes when they store that information, how they function. All right, we'll get to that difference later. For now, let's have what we call an SRLH. So these are these are basic elements of storing information. Difference between them being in the way the state changes, the way the state changes. We have what we call an SR latch. What is an SR latch? It is an element of storing memory, an element of storing information. It is a memory. All right. For an SR latch, we have something like this block diagram. S, these are the inputs. S and the R, we have the outputs Q and Q bar. Is that true? Yes, it is true. Sometimes it can look like this, S, R, Q bar, Q. And this one is called an active low. This one is called an active high. All right, 10 minutes. So these are my SR latches. 2 inputs, 2 outputs. S and R, Q and Q bar. Q bar meaning Q naught. Right. When Q is equals to 1, right, when yeah. Where are we in Africa? Right. When Q is equals to 1, this means Q bar is equals to 0. This means we have what we call the set state S. When Q is equals to 0, it means Q bar is equals to 1. It means we have the reset state. I'm thinking this is where the name came from. SR latch, set and reset. However, no, we are not on the however part yet. Now, whether on set or reset state, the latch will continue to remain on the same state as long as the power is not switched off. Is that the point? Nope. All right, we are done here. We have the set and the reset states, two states. Set Q is equals to 1. The output, when the output becomes 1, we have a set. When the output becomes 0, we have a reset. We have the logic circuits of these SR latches, the logic circuits. We have one which is NAND gates only, another NAND here, and I have my output Q, another NAND here, I have my output Q bar. This comes here. I have another NAND, right? So this is my R, this is my S. Voila. Active low. This is an active low circuit of the SRLH. The block diagram right here. What is inside here is this circuit there. Two inputs S and R, two outputs Q and Q bar. Nuns only. Universal logic gate. We have another one with NORs. So this one, it looks like this with a NOR gate, output Q bar, another NOR gate, output Q. I have my S, I have my R. This is right here. This is right here. You can see there is feedback somewhere there. That's why it's called the sequential circuit. There is feedback there. The output comes and becomes an input on another gate. That's why it's a sequential circuit. There is feedback somewhere there. Right. These are the two forms of the SRLH. One being of NAND gates only, the other being of NOR gates only. The truth table for this, the truth table for these circuits, the truth table, we have two inputs, S and R. We have output Q plus. Output Q plus. I'll explain what Q is. All right. 0, 1, 0, 1, 0, 0, 1, 1. You need to understand the truth table of this latch. For all the memory elements we are going to be doing, you need to understand how we came up with the truth table. The truth table is like this. For if S is equals to 0, R is equals to 0, we have what we call the memory state. We have what we call the memory state. What does the memory state mean? The memory state means whatever the input is, it will remain on the output. The memory state, it holds. Whatever the input is, it remains in the output. So if, for example, the input was Q, it remains Q plus the next state. Q plus this is the next state will remain as Q. If the input was Q, the next state will remain as Q because we have a 0, 0 here, the memory state. If our S is equals to 0, we call this the reset state. What this means, whatever the input is, the next state will be 0 because of this reset state. When S is equals to 1, we have the set state. Whatever the input is, your sequential circuit will be set, the output will be 1. And for this state, this is an illegal state. It doesn't happen. It doesn't happen in an SRLH. In the next session, I'll be explaining how we came up with this truth table and how the SRLH functions. You need to understand what is on this truth table. When we come back for the next session, I'll make you understand what is on that table. Claim it as it is for now. The next stage will be on the understanding. Questions, comments, 2 minutes. Questions and comments? Nope. Nope. So join me in the next session.
No questions.
All right, join me in the next session soon after. Soon after.